Solid state transducers. This will be covered in chapter 8, which basically covers the some of your basic transducers, and then chapter 15, we'll get into our photonic or photoelectric transducers. So I thought I'd cover both of these at the same time instead of dropping back later on in the semester. So a solid state transducer. So basically a transducer is what most commonly now we refer to as a sensor. But these two terms would be used interchangeable. Now, of course, the other day we went over some of the things that we might want to sense. So this may include things like position, where something at, speed, how fast something's moving, the weight or the force being applied to something. We need to be able to count things, sense pressure, sense how fast fluids are moving, sense temperature, which we even do that in our house if you've got a thermostat on your HVAC system. Might need to censor the brightness, the color, and the intensity of light, how thick something is. We might need to sense time, gas levels, which is covered in the book, liquid levels, motion, if something's been moving, if you got like a motion detector on your house with floodlights, orientation, how it's oriented, the shape, the size, proximity, which means what's it next to, moisture and viscosity. Now, this is just a basic list. There anything that we could probably come up with that I can sense, that I as a human can sense, odds are we can make a sensor or a transducer to sense that for us. Now, this is what's covered in Chapter 8. Chapter 15 covers photonics, but Chapter 8 covers thermistors, photoresistors, Hall effect sensors, ultrasonic sensors, and piezoelectric or piezoresistive or PC. I think the book refers to them as piezoelectronic sensors. So this is a thermistor, and we've already talked about this the other day in class because most of y'all answered questions about thermistors. And we know now that we have two types of thermistors. Okay, so thermistors, these are resistors that dynamically vary their resistance with temperature. Dynamically vary their resistance with temperature. We have two categories of these. We have NTCs, which are negative temperature coefficients. The resistance of these devices varies in the opposite direction of temperature. So it means if temperature goes up, if you got an NTC thermistor, its resistance will go down. And these are the only ones we have in lab. If you got, but we'll be doing some experiments on these. We have a handout lab on transducers, and we'll be looking at some photonic transducers, some photoelectric, some different transducers. We'll let y'all play around with a little bit just to get a feel of it. But the only thermistors that we have are NTC thermistors. Also, there are positive temperature coefficients, or PTC transmistors. These devices, the resistance varies in the same direction as temperature, which means if temperature goes up, the resistance goes up. If temperature goes down, resistance to these devices go down. Unfortunately, these things are not linear, which means when their resistance change relative to temperature, and this is the figure 8-3 in the textbooks, which gives us an example of a NTC thermistor, is that over here on this side, of course, we have temperature, and on this side we have the resistance. This was in ohms, but this would vary depending on what type of thermistor that you have. And notice as the temperature goes up, okay, resistance goes down. So here it says at roughly 190 degrees, if we was to drop this down, we would have pretty close to 0 ohms. And as the temperature goes up, so the way we would read these, if I come over, if I put a horizontal line and then I drop a vertical down to the other one, then that means this thermistor at 120 degrees would have one probably around 38 ohms. I'm just taking a guess at that. So, but you can see as it goes up, if this was what we call a linear device, which means it varies in a straight line, then this would look something like that. This guy has sort of what we refer to as an exponential curve, which means it varies with the natural log of a number, which we're not going to get in here. But notice this varies in a curve. Now, what we do to make these things appear to be accurate is, number one, one thing they're going to do, normally when you buy the thermistor, when you look at the data sheet, you can get this curve. So we could, if we knew the data sheet and we entered a table, then we could, of course, look this up with a computer or some type of processor. So our computer would come in and it would use the curve and actually display an accurate temperature. Another way that we can do this is, if you think about a residential house, we may run our temperature, if you're real warm-blooded, you might run it at 100 degrees between here and, 80 and 60. Well, if you look at the curve along this line, between those two spots that are close together, the temperature is fairly linear. So let me put this back up here again and show this to you. So let's say my house, I'm a cold-blooded person, so I run it, my house at 80 degrees in the summertime, and then I like to sleep in real cold weather, which I really do. So if I draw this over, then we notice that this point in between that is pretty linear. So this is what, if you have a thermostat in your house, a digital thermostat, it's going to use one of these thermistors in there, but this guy is really accurate, or pretty accurate, because we limit it between the range where we're going to run, require the thermistor to operate. Now the problem is that when we try to get an input on these things, there's three quantities we can get from a sensor, but two of them are real hard to, two of them are hard to measure. One of the things is that we can get a voltage, or another thing we can do is we can vary the current. And of course, the next thing we can do is vary the resistance. Now, normally we don't do this. So what we're doing, normally we got to get a quantity we're going to have to measure. So usually we do the current or we do the voltage. So if I was to come over here and take a thermistor and put it into a DC circuit, and then I came over here and I put my thermistor. Okay. Now normally what they'll do is they'll come over here and they'll put a little symbol and put an F for Fahrenheit or a C for Celsius or centigrade, or they might put a T in there indicating this is a thermistor. Normally we put this thing inside a circle, which indicates it's solid state. Okay, and then we'll come over here and we'll put that right there. Well, the problem is, if this right here was 12 volts, even though the resistance was varying in the temperature, this is the only element in a series circuit, so it would always measure 12 volts. So what I would have to do is somehow, I would have to come up with a means to measure the current. Now, the current would vary with temperature, but current is real hard to transmit, real hard to receive. So normally what we do on this, and we'll look at another method that we do, normally what we do is we come up here and we put a resistor in series with it. So this is an NTC. So what happens if the temperature goes up, its R goes down. And Kirchhoff's voltage law says the sums of the voltage drops in a circuit has to equal to the applied voltage. Well, if this resistance goes down, let's say it's 2 volts and we're sitting here and this is 100 ohm and this is 100 ohm. Well, what would happen is that my output right now would be 1 volt, because 100 ohms, 100 ohms, we have to drop the equal voltage. So this drops 1 volt and this drops 1 volt. But if the temperature goes up, then what's going to happen is this right here might go down to 50 ohms. Well, if it goes down to 50 ohms, okay, then what that means is that now, if we do our voltage, so before when we did our voltage divider formula, so VR, this is going to be R, would be equal to the size of R, which is 100 ohms, divided by the total resistance. Well, the total resistance was originally 200 ohms, and then we would multiply that times 2 volts, and this would come up and give us 1 volt. Right now, we're dropping this down to 50 ohms, so now VR is going to be equal to 50 divided by 150. So that's going to be 50, the size of the resistor, 50, divided by 150, and then I put equals, and then I'd multiply that times my voltage. So it meant now the resistor, the output of the resistor would have dropped down to 600 and, I did that wrong. I went across the wrong thing. This is still 100, so let's go back and clear that out. So sorry, guys. So the one we want the voltage drop across is not the 50, not what the thermistor is doing. What we're looking at is what's going on with R. So what we would do is we'd come over here, and if R is always 100 ohms, but now my thermistor has dropped down to 50, so that's going to be divided by 150. So the voltage drop across this, because this is where we're taking our output right here, and we're calculating the voltage drop across R rich, times we haven't changed the voltage. So when I do this with my calculator and I do it right, it's going to be 100 divided by 150, which is the total resistance of the two, equals, and then I would multiply that times 2. So now this guy right here is dropping 1.33 volts, and this guy right here is dropping 1.666666. So we're not disproving Kirchhoff's law. But what I can do now with this resistor right here is I can vary a voltage that represents temperature. Okay. And then that's what they're showing in this circuit right here. So what I have here is I have a thermistor hooked up. Let me find my camera. Okay. So this is a thermistor, and we'll look at several ones right here. And what I have is I have my ohm meter set up. So at room temperature, I guess it might be, I don't have a thermometer, I really need one. So right now, we're probably sitting around 73 degrees in here, maybe 70. And notice I'm going to come over here and just take the heat of my finger, and I'm going to start touching this thing, and you notice the resistance starts going down. And I take my finger off of it, and the resistance starts going up. Now, of course, this right here is a sure enough heat source. This is a soldering iron that I've got plugged in. And you can see the temperature starts going down. And I'm not touching this, guys. I'll put it off to the side so y'all can see. And eventually it would come up here and stop, depending on the temperature of the soldering iron. And by the way, we have soldering irons that you can control the temperature. Well, how do they know the temperature? Well, they use a thermistor that's actually in the temperature, the head of the heating element here, that we can use to control this. Okay. But the problem is, I can't see what's going on as far as getting a voltage out of this. So what I have here is I have a 20 k ohm resistor. So you can see this guy right here is pretty high, but we should still be able to see that. And I'm going to use a 5 volt source. I'm going to come over here, and I'm going to put my meter on volts, okay, DC volts. And I'm going to move a common across my resistor. So my meter is across my resistor right now, and I'll come over here, and this is my positive 5 volt source. I'm going to put this to my thermistor and turn on my power supply. Of course, now you see it. Now we got a voltage output. Okay. Now what should happen is when I heat this up now, the voltage should go up. And I cool it down, let it cool down, the voltage will go down. Okay. And of course, here's my soldering iron now. I'm going to bring it over here. You can see I'm not touching it, even though it appears I am, but that would be melting my. So now what I've got, now notice now the voltage is going up because the resistor is at the bottom. So the resistor, the fixed resistor, this is common. There's my black lead off my power supply. So now I've turned a NTC to give me a positive voltage when temperature goes up. Now the problem we have is that first of all, these actually have no meaning unless I know the voltage that this thing gives me at a certain temperature. But the problem is that, let's say, normally when we measure temperature, we measure it relative to a temperature. Normally that would be 0 degrees. Of course, the problem we have with the Fahrenheit scale is freezing is actually 32 degrees. And this is why I prefer the centigrade scale when it comes to temperature. So what's nice about the centigrade scale is that when we've got 0 is freezing. So what that means, if I could take this thermistor and put it into something that's freezing, and normally what they would do is they would put this into a cup of ice water, stirred up real good, and they would immerse the the thermistor down into the ice water, and then now we would have a voltage that was relative to 0 or freezing. So what we did there, to be able to do this electrically, what we're going to do is, I'll see where it's at on the PowerPoint slide, is we use a circuit, and hopefully y'all looked at this a little bit when you were in DC. We refer to this as the Wheatstone Bridge. And why? Because it was originally developed by Charles Wheatstone. And he did this as a method of measuring and calibrating equipment and stuff like that. But what we do here is we normally use this in just about any sensor or transducer that varies its resistance with what it measures. And we need to be able to set a reference voltage. Then normally what we do is we use a Wheatstone bridge. So the purpose of a Wheatstone bridge, and I'm going to go over to the next slide, is we have the ability to set what we call 0. Now the way a Wheatstone bridge works, and I'm going to draw this easier for me to draw, is I'm going to draw it as just a series parallel circuit instead of drawing it in the diamond shape. So this is another way we can draw it, and this is a lot easier. And of course, this is my Wheatstone bridge right here. Anytime we need a connection, we need a plot. So what I'm going to do right now is I'm going to come up here and use all the same size resistors. And these are all 20K ohm. But where we take our output is we take our output right here. So I'm going to come over and I'm going to put a voltmeter right there. Now, one of the things we learned about in series circuit, if you got resistors that are the same value, then they drop the same voltage. Another thing that we learned is that the sums of the voltage drops have to be equal to the applied voltage. So to make this easy, what I'm going to do is I'm going to come over here and put this across a 10-volt source. So that means each one of these resistors have to drop the same voltage, over here, right? And the sums of those voltage drops have to be equal to the applied voltage. So that means this resistor up here is dropping 5 volts. This resistor right here is dropping 5 volts. Now what I'm going to do is I'm going to come over here, I'm going to measure between these 2 points right there. So what that's going to do is that's going to put plus 5 volts right there. This is dropping 5 volts. This is dropping 5 volts. That's going to put plus 5 volts right there. Now, what's the difference in potential? Now, most people here, for some reason, and I don't know why, they want to add these together and say 10 volts. But when we talk about a difference of potential, I have a plus 5 volts minus a plus 5 volts. This is the difference. So we come up and we get 0 volts. Now what we do here is we say the bridge is balanced. So that means the ratio of these resistors must be the same. They don't have to be the same value, I should let those alone. But they got to have the same ratio. So let's say over here I put a 20K, and over here I put a 50K. And over here I'm going to put a 1K, and over here I'm going to put a 5K. Now, is it balanced? Well, some people say it's not, but what we're doing is calculating how much voltage, and what we'll do is we'll look at this resistor right here. So using the voltage divider formula, we say VR, so these are the two resistors we're going to reference to calculate the voltage drop across. We'll call this R1, we'll call this R2, we'll call this R3, and we'll call this R4. So I'd say VR2 would be equal to the size of R2, which is 50K, divided by the sum, which would be 70K, and then I'm going to come up there and multiply that times 10 volts. Now, we learned in algebra that the 5 would cancel out and the zeros will cancel out, so that's going to be 5 divided by 7. So I'm going to come up here, I'm going to take my calculator, and I'm going to say 5 divided by 7 equals this, and then I'm going to multiply that by 10 volts. So that means 1.14 volts. I'll just round that. So this guy's dropping, this would be plus 1.14 volts. I'm going to go back and double check that. 7.14 volts. Good thing I did. 7.14 volts. Now, if I come up here and get 7.14 volts right here, that means this meter would measure 0 volts. So VR4 would be equal to 5K divided by 7K, and there it is. We already know it's going to be there, right? Times 10. Well, over here, the K's cancel each other out because they're on the top and the bottom, which means this guy right here is going to drop 7.14 volts also. So it means my meter would measure 0 volts, so the bridge is balanced. So what we're saying is that the ratio on a Wheatstone bridge, if the ratio of these two match the ratio of these in the correct order, in other words, I'm using little big, it could be big, little, so it has to be the same order over here on which resistor, where you put the big resistor and where you put the smaller resistor. But as long as the two ratios match, then we will have what we call a balanced bridge. Well, my thermistor has a resistance of about 100K. And what I'm going to do is I'm going to come up here, and I erased one of my resistors, but I can take care of that real quick. And you're going to run into the Wheatstone bridge all over the place because using sensors that vary their resistance with what they measure. So I'm going to put my thermistor, I'm going to put it on the bottom just because it's easier. So I got my thermistor over here, right? And it varies its resistance with temperature. Up here I have a 20K ohm, R1. Right here I have a 20K ohm, R2. And then what I didn't have down here is I've got a pot that I'm going to wire to act like a rheostat. So let me use the right symbol there. I fussed at y'all about some of y'all doing this. So I've got a pot wired as a rheostat. So we wire a pot as a rheostat. We take this unit right here we call the wiper, and then we come up here and we connect it to one side. And I showed y'all the other day, all that varies is which direction we turn. Now what we can do right here is, let's say, so 100K at room temperature. So let's say this thing goes up to 250K. I can't do it that way. So what we'll do is, let's say I can't immerse it in water. So I'm going to say, what I'm going to do, just give y'all an example, is I'm going to say this is 100 K at 0 degrees centigrade. Now, to reference this, what I would like to do is I would like to balance this out, right? You understand? Let's say I don't have a pot. The biggest pot I've got is a 100K pot. I'm going to pause the lecture for a second and let me find a thermistor that has a smaller resistance than 100K at room temperature. Okay, I found another thermistor. I'll show you that in a second. But this thermistor has a room temperature of about 10K. So what I'm trying to show y'all, or trying to show y'all, is that using a Wheatstone bridge, but what we'll say at 0 degrees. So I give you, so what I've done is I'm simulating immerging this into a glass of ice water with ice in it, not just cold water. It's got to have ice in it, and not melted ice. It's got to actually be ice cubes, nice ice cubes in there. And what I can do is that if this is 10K, what I can do now, and these are balanced up here, and they don't have to be perfectly balanced anymore because I'm going to compensate for that. So if this is a 5% tolerance and this is a 5% tolerance, it'll always have the same tolerance, but all we have to do is set the same ratio between this side and that side. Now what I'm going to do is, what I have the ability to do now is I can set the ratios. So right now what I've got is I've got my meter set up. It's directly across the input like I showed y'all. Okay. So my meter is connected. So here's my Wheatstone bridge. So here's a 20K. This is a 20K down here. So I've reversed them because I wanted a positive voltage. Okay. Here's my thermistor, and here's my potentiometer. So right now, I'm simulating and merging this inside of ice water. So what I can do now is I can come over here on my potentiometer, and I can adjust this to balance the bridge, wrong way, Rich, and I'll adjust it till I get 0 volts. Now, as soon as I get 0 volts, and this is the big advantage of a Wheatstone bridge right here, is that we can use a Wheatstone bridge to set a 0 reference. Okay. So now I've got a 0 reference set. I'm off a little bit, but anyway, now I'll come over here and I'll use my solder 9, and now this voltage means something. So now the voltage goes up. So now 11 volts would actually represent a temperature relative to 0 volts, right? I mean 160 millivolts. And then of course, if it goes down, it goes down. Let me change the range on my meter. Okay. So we use this a lot for I'm not going to say any, most transducers that vary their resistance with what it checks or what it measures use a Wheatstone bridge. Why? Because that way we can come up and we can set what 0 is. What's our origin? Where are we starting measuring this temperature from? By the way, there are some solid state temperature sensors, an LM34 and an LM35. I think the LM34, one of them's centigrade and one of them's Fahrenheit, but these are integrated circuits. So they primarily use a thermistor inside, but they compensate for the non-linearity of the thermistor. These guys are very, very accurate. I've got one. It looks like a transistor. It's got 3 leads on it, and I think we've got the data sheets. I'll make sure we put those in there. You probably can't get those locally, but you definitely can get them online if you wanted to set up a circuit that actually measured true temperature. And what you'd use is use those integrated circuits. So this is basically a thermistor. So we got several types, and all ours are NTCs. So this is the one I originally had, and this guy here has about 10K at room temperature. This guy right here had about 100K at room temperature. And then we have these right here that I haven't hooked up yet. These looks a lot like capacitors, but these are NTCs. NTC 10. We can look this one up and probably get the data sheet on it. So that's probably what I need to do, and that way we could know, and I can show you all the actual chart, the chart for true thermistors. You'll run into these things all over the place. Like I said, using electronics, we can compensate for their non-linearity. If approximate temperatures are needed, then these guys work great, especially if it's used over a narrow range, like in your HVAC system you have at your house when you run your temperature, or when you run your air conditioning. So this is the Wheatstone Bridge, guys. I know it looks a little different. This is actually wired up and not the one that's actually drawn, but at least we understand. So if the Wheatstone Bridge is balanced, then we get 0 volts across this guy right here. And that's where my meter's at. The only difference is I put my thermistor up here at the top, so my voltage will go positive. So we got another device that varies its resistance, but this guy here is called a photoresistor. Just about everybody calls this a photocell. And we use these guys all over the place too. These are solid state devices, and these come in different sizes depending on the amount of current you want them to conduct. I thought I brought my whole package out, but in Dowling I didn't. These are bigger anyway. They're big to small, and in the images that we got down there, the images that I pulled off the internet are pretty straightforward. So what we got is, let me turn my power off, my power supply. Okay, and this guy here. So here's a photoresistor. You can see if I get it out of the glare. So it's got a clear coating on it. I don't know exactly what it's made out of, but this is a semiconductor. It just comes down through here and runs down back and forth, back and forth, back and forth, back and forth. Now this guy is a photoresistor, or most people refer to them as photocells. And what this guy does is it varies its resistance with light. So I'm going to put my meter back on R, and we'll see what this guy does. I'm just going to come up here and take my meter and hook it across this thing. So right now it's showing an overload. So it's definitely got more than 200 ohms. Okay, still not measuring, or did start measuring. Now, of course, this is really going to vary. So you can see this guy here is already jumping around because undoubtedly it's seeing different levels of light. But what I'm going to do is I'm going to come over here and cover it up. And notice as I cover it up, the resistance goes up. And then as I start uncovering it, the resistance starts going down. Let me get something opaque, or something that's going to block a lot of light so I can slowly do this. So notice if I come over here, let me fold this up again. So I'm going to try to get through it at all. Okay. And then I come over here and start covering it up. So right now it's got about 560 ohms, right? And as soon as I start covering it up, notice the resistance goes up. Okay, so this is going up to 1.8K. So we can probably run it right here. Okay. And then if I come over here and start uncovering it, then the resistance goes down. You can't say it has a negative temperature coefficient, but it works similar to an NTC thermistor. Okay, so right now it has, and of course, cover it up, resistance goes up, uncover it, the resistance goes down. Okay. Now, we use these guys here all over the place. I think I was explaining to y'all the other day, and it might have been another class. I might have got it confused. Is that in the old days, before they came up with these photo cells or these photo resistors, all the parking lot lights and everything, it was on timers. Well, you know, we go through changing seasons, and so here we automatically just this weekend changed to what we call daylight savings time, which means we moved our clocks ahead 1 hour. Well, what the people at the stores and all, well, they'd have to go all around and retime everything. They'd have to change all their timers so the lights wouldn't be coming on at 5 o'clock before it was even dark. Now they don't do that, but some older stores, you can still see this. You know, if you go class of plates and here it is in the summertime and it's 5 o'clock and the lights are on out there, then those guys are still using timers. But now what they do is, if you ever looked at the top of these things, or then they've got this photo resistor. Of course, there's electronics to it. There's no way in the world this guy right here could control a street light, but it can be the sensor that controls the street light. So this sensor could pick up a relay, and the relay could run the street light. Okay. So all our lights outside now come on automatically at night, and they go off automatically when the light comes out. I mean, when the sun comes out. So these guys are all using photoresistors. Your cell phone, if it varies the intensity of the flash, then it's got a photoresistor in there. Probably a phototransistor, which we probably will touch on. Y'all remind me to touch on that when we get into bipolar transistors. We're going to look at a photodiode, but not a phototransistor. But these devices use to sense light, and of course, to do different things. So this is a photoresistor. Of course, this varies its resistance with light. So what I would have to do to get a voltage out of it, I'd have to put a resistor in series with it, just like we did with the thermistor. If I wanted to set a reference, a 0-volt reference or a zero light reference or a certain light reference, then of course we would hook it into a Wheatstone bridge. Okay. So those are photoresistors. By the way, their size is just like resistors. They're rated in watts, and if you exceed the wattage rating of the photo resistor, then it's going to burn up, and it won't work anymore. If it does work, it's not going to work the way it's supposed to. You know, you need to make sure you don't exceed the wattage rating on these devices. Photoresistors are what most people refer to as photocells. And these are the symbols, by the way. So normally when we put a circle around a symbol, it means that it's solid state. And of course, when we use that term, it means it's made out of a semiconductor, right? Uses the property of semiconductor. This is probably the one you're going to see most often. This is the symbol we use over here in the United States. This is the ISO symbol, or the international symbol of a resistor. But notice they draw the arrows pointing in. So when you see arrows doing like this, it means it's receiving light. If you see arrows coming out, it means it produces light. But these things should be inside of this is a generic symbol, by the way. This could represent a thermistor. This could represent a photoresistor or any other device that varies its resistance with temperature. A photoresistor. The book gives some excellent examples on applications for these devices. So you still need to read the chapter on this lecture to get all the different applications. I'm not going to go over all the applications of this. The next thing we'll look at is what we call a photovoltaic cell. Photovoltaic cell. That's the technical name for it. Just about everybody calls these are solar cells. Photovoltaic cells or solar cells produce a voltage that is proportional to the amount of light that strikes the cell itself. And we're not going to get into the theory of how this operates. If you want to get in there and look at that, you're more than welcome to do that. But basically, it absorbs the energy of the photons coming in from the light and turns it into an EMF. By the way, this is the symbol of a solar cell or a photovoltaic cell. Okay? These are some photovoltaic cells that we have available that you'll play around with in lab. So here's our solar cells that you'll be dealing with in lab when you do the lab on transducers, and that's a handout lab that we'll be doing after you get through with your power supplies labs. And I'm going to put my emitter back on volts. Okay, I'm going to put it on 2 volts. You see it's got a polarity marked on here, minus and plus. Won't hurt your meter if you hook it on backwards. So I'm going to come up here and hook up these tabs. And you see this guy here is putting out around 250 millivolts. If I cover it up, the voltage goes down. If I take it away, the voltage goes up. Of course, the higher the intensity of the light, the more voltage these are put out. We've got a big solar panel over in Building A. I need to get it and bring it over here. And that guy puts out a pretty good deal of voltage. You can see with enough light, this guy here can put out almost a half a volt. Right now we're under fluorescent lights. I'd imagine we could probably get around 2 volts on a nice sunny day out of these things. But these things vary with light. Now you see these guys all over the place. I mean, the sheriff department has got these flashing lights they put out, and they got. So what we normally do is we use we can power up directly off a solar panel. Okay, I think Harbor Freight sells a 40-watt solar panel. I don't remember how much it is. But normally what we do is we use the solar panel to charge batteries. And then at night we use the solar batteries to provide the batteries to provide the work. Okay, does that make sense? So you'll see when you're out on the interstate and you're driving along, you'll see these lit signs that are out in nowhere, and there's no power running to them. But if you look off to the side, every once when you drive it, you'll see a nice big gray box, and you'll look and see the solar panel on top of that. So what they're doing is that during the day, they're charging up those batteries, and at night they run the lights off the solar cell, which is pretty nice. And there was they have a competition every year. It's a green competition where they actually race solar-powered cars. Of course, they can only race during the day because they're running directly off the batteries. There was a plane that made a world trip running its motors off of nothing, and it was unmanned, by the way, running its motors off of solar cells. But they had no problem there because these guys were up above the clouds, and they did charge batteries. I'm sorry. So they either ran it off the solar cells or charged the batteries. So which was a pretty neat situation. So they ran it off the batteries at night, and then they ran it off both of them during the day. But and they're talking about putting these drones up above the clouds, and basically they could stay up there forever because they don't need any fuel, which is pretty neat because they're going to run off of solar power. But this is only one cell. I think it's one cell. So what we do to increase the voltage output of these things, we treat them just like we would treat a battery. So this is labeled Wheatstone Bridge, but I'm going to come up here and erase that so I can draw on this blank slide. So regular batteries is we hook them in series. So first of all, people don't understand what a cell is. And a cell is just one unit of the battery. So this is a misnomer. We've been calling these things wrong, and it's the commercial or the consumer market that set this. But most of your batteries are actually should be called sales. So we have a C sale, we have a D sale, which is just a bigger sale. We have a double A sale, and then we have a triple A sale. And what we do on these different sales, of course, and you can see these in your remotes or whatever, is if I want to increase the voltage, then what I'll do is I take multiple sales and I hook them in series. So standard out of an alkaline cell is around 1.5 volts per cell. So if I hook 4 of them in series, then if I measured all the way across the output, of course it would measure 6 volts. So we hook them in series to increase the voltage. We hook them in parallel to increase the current. So if each one of these was rated at 1 milliamp, then what I would get out of here, I would get 6 volts, but it would still only be at 1 milliamp because they're in series and the current is constant. If I want to get more current, then what I do is I come over here and I hook my batteries or my cells in parallel. I'll say batteries, but these are just DC cells. Okay. So since they're in parallel, then we don't get an increase in voltage. So I'd have 1.5 volts out, but now I would have 4 milliamps. So what we can do, and you can see this sometimes on your remote, some of the batteries are hooked in parallel to increase the voltage, series to increase the voltage. Some of them's hooked in parallel to increase the current. And that's exactly what they do when they build these big old solar panels. They're rated at a certain voltage using a certain lumens or a certain amount of light at a certain current. And how do they get that? Well, they build the voltage up by hooking them up in series, hooking the cells up in series, and then they hook them in parallel to get current. By the way, battery means a group of. So a battery would be a group of cells. So a D is not a D cell. We have D cells, we have C cells, we have double A cells, and we have triple A cells. Okay. Now consumers don't understand that, so they started calling them batteries. So now we call them batteries. The only true battery is a 9-volt battery, and it's made out of 6 cells hooked in series, which gives us 9. And they're 1.5 volts, which gives us 9 volts. So if you ever tore one of those D batteries apart, you'd see there are actually a group of 6 of them in there, and they're stacked on top of each other, right? The D cells, and then yeah. So that is actually a true battery. Your car is a battery. Your car has 6 cells. It's lead acid. We get so 6 cells gives us about 2 volts per cell. So that's 12 cells. That'd be 12 volts. And now they've got a bunch of cells in parallel. When we say 6 cells, each cell has tons of cells. So if you ever looked at those down inside a battery, you'll see they're in groups of plates. So they're hooking them in parallel there, and then they go between them. That would be, then you have each isolated from each other, and that would be the 6 different cells. So that's why you get 12 volts out of the battery. So we use these guys to charge things. You can buy solar chargers if you're a camper and you get out where you have no service. Then what you can do is you can buy solar chargers for your cell phone. Now it takes a little while to charge them, but hopefully you don't go camping to set on your phone all the time anyway. Normally when you go camping, what you should do is, stay off your dang phone and but charge it up overnight, and that's the way you'll have your phone in case of emergencies, in case you get lost. It's always nice to have a fully charged cell phone, because now if you've got cell service, then odds are they can pretty much well locate you by your cell. So we'll come up here and we'll hook up a couple of these in series just to show you that the voltage does go up, but we're not increasing the current, we're increasing the voltage. So here's another one right here, and I'll get a jumper. And of course, when you hook them up, you have to go from negative to one into the positive of the other, or vice versa, right? And then I'll come up and hook my meter back up, and hopefully we get about 400 millivolts. And we do. So in fact, we're getting 500 millivolts. So now we're getting about a half a volt out of two of them. Now, of course, we didn't increase the current capability. So if I tried to load this down with like an LED or something, odds are the voltage is going to drop down because these are not regulated. So that's another consideration you got to have, is that these guys are not regulated, which means they vary with load. And so their output will vary with load. Isn't that neat? But these guys here output a voltage that is proportional to light. Next thing we're going to do is look at a Hall effect sensor. This is a true integrated circuit. So a Hall effect sensor varies the voltage proportional to a magnetic field. Proportional to a magnetic field. This is an electronic circuit. Electronic circuits don't work off anything, so they're going to have to be powered by an external source. We use these for proximity sensors. We use them for position sensors. We use them for speed detection, and also we use these to sense a DC current. So if you've got a clamp-on ammeter that's got a DC current measurement that you can measure with the clamp on, then this right here is a Hall effect. Now, these guys here are going to be different things, and they're going to be fairly small, depending on how much current they're going to measure. Now, this is our Hall effect sensor. It's got 3 leads on it, but it's an integrated circuit. And then two of them will be the power pins, and then one of them will be the signal pin. I'll have to get the data sheet out and look it up in a second. And this guy right here is what we call a latching Hall effect sensor. So what this does is we'll bring one magnetic field up to it, and it'll turn on. And then we bring the opposite magnetic field up, and it will turn off. So latching means it's going to hold it until once you turn it on, it's going to stay on until you turn it off. So this kind of works like a manual light switch. Once you go over and flip a light switch, how long does the light stay on? Well, it stays on until you turn it off, right? You understand? But here we're going to turn this switch on, and we're going to turn it off with a magnetic field. It's going to take one magnetic field to turn it on, and it's going to take the opposite magnetic field to turn it off. The other type we have is what we call a proportional magnetic Hall effect, which has a little cheaper because this has the circuitry in there that latches. But these will actually give you a linear output, a voltage output that represents the strength of the magnetic field. I'm going to pause the lecture while I come in. So we have a Hall effect sensor called an HI300. And this is the actual internal block diagram of it. So right now it doesn't really make any difference to us. But this is a guy called a transistor. It's an NPN transistor, and this is the actual output, which we'll be talking about in the next lecture. So what we have here is I have my Hall effect sensor right here. Okay. And what I have is I have a light emitting diode, which we'll talk about later on. And then I've got a 330 ohm resistor, and then I've got a magnet. This is nothing but a magnet. Okay. And I don't know which is north south, but anyway. So all I'm going to do is I'm going to bring my magnet up to the Hall effect sensor, and you see the light turned on. I can keep bringing the same polarity up there, and nothing happens. I'm going to turn the polarity around. Now I'm coming in with the opposite polarity, and when I get it close, the the light turns off. And this is what we mean by latching Hall effect. Larry was telling me about a system they have at Mercedes where a cart's moving down and it goes past one magnet and the cart speeds up, and then it goes down another magnet and it slows down. Well, that's basically nothing but a Hall effect sensor on the cart, and they have magnets out there. And when it comes back, one of them uses a north and one of them uses a south, so the PLC that's running the cart knows when to speed it up and when to slow it down. Ain't that neat? Okay, that's the same polarity. Okay, so this is one polarity, turns it on. The other polarity turns it off. And this is what we do by latching. So latching, the LED stays on until I do what? It's going to stay on until I turn it off. Let me put the magnet on my X-Acto knife and see if we can do it this way. Off, on. So here it comes in this direction, turns it off. I'm going to flip my X-Acto knife around. Of course, it's got a magnetic field there, and this turns it on. And we call this a latching Hall effect. So that Hall effect is sensing the magnetic field. It's not sensing the metal, it's sensing the magnetic field. Now we can make it appear to sense metal. So odds are this is the guy that's sensing the speed of your, if you got an RPM or tach gauge inside your car, odds are this is the guy that's actually sensing the speed. Okay. This is just showing you maybe there's two magnets. One of them will be north. And this one is a regular one. This is not a latching type. And of course, if this is a Hall effect sensor, then we can use this. How fast these pulses occur, we can come up here and use that to sense speed. This is basically a Hall effect sensor. This is not the same one we've got. But we have to power these things up. So this is plus 5 volts. I think the one we got can go up to like 15 volts. The HI300 that we're using can go up to around 15 volts, 12 volts at least. This one undoubtedly works off 5 volts, and I'll look and see if I can get one that's not a latching one like the one that we got. This is the way we can. So the Hall effect itself senses a magnetic field. And so anytime the magnetic field moves past the Hall effect, then we can get a pulse or we can do something like that. What we can do is put a magnet and then put a Hall effect sensor and then use the Hall effect sensor. Then we use the metal actually comes in and concentrates or changes the magnetic field. So here when it hits the gap, it would see one magnetic field. When it was over this part right here, it'd see another magnetic field, and we can use that to figure the position of this notch. Here we're sensing metal balls, so this is a steel ball, which is magnetic. Here we're using the same situation where I have a permanent magnet sandwiched between the permanent magnet and what we're trying to sense is a Hall effect sensor. So when the ball moves across there, it concentrates the magnetic field through the Hall effect sensor, and we can use this right here. We can literally get pistons now, hydraulic or pneumatic pistons that we use to move things. And they literally now, most of them, a lot of them out here, they'll have the actual puck inside there will have a magnetic ring around the back of it. And then what we can do is we can put Hall effect sensors up here, and we can sense when the cylinder is extended or retracted. And when I get back from Germany, we'll go over to the manufacturing line and look at all the Hall effect sensors that they use to sense when those things are extended and retracted. They use a Hall effect sensor or reed switch. A reed switch is electromechanical, so we're not going to talk about this. This is solid state. Ultrasonic sensors. Now, this is truly an electronic circuit, and we're not going to really get into actually how these things work. But basically, they work on sound. So they send out a pulse of sound. And then when it hits an object, what it does is it reflects back. And this is what they use to detect whether something's there or not there. And also, we can use these guys to detect distance. So these are our two categories. Can be designed to sense distance, movement, the levels of liquids and solids. They can use to be set speed. We call it the Doppler effect, and also the direction. We have two modes we can operate in them. We have what we call a diffused mode, which is basically what our line uses off. So diffused mode, we would send our pulses out, our sound pulses back, and then we would wait and see how long. Then we'd see how long it takes from the back to bounce back. Here, your emitter and your receiver are inside the same unit, and then of course this would send this information back into either a PLC or what. Then we have what we call the direct mode, where they come in and the emitter and the receiver are two different units. And what we're doing is we're bouncing this off, right? And if something comes in between these two units, then the receiver would no longer receive the pulses. So this is two modes of operation. We have what we call the diffuse mode and the direct mode. You need to know those. We use these guys to sense distance. So it's very, very popular now. So my wife's van, it's got two side mirrors on it, and then it's got a camera on the back, and then it's got all these little ultrasonic sensors back here. So if you start backing up and if you're going to run into something, you start getting an alarm. Over here, if a car starts passing me and gets in my blind spot, then there's a light that comes on indicating that something's over here on the side. Your self-driving cars are using a lot of optics and ultrasonic sensors to sense things around them so you don't run into things. We have automatic brake systems now that use ultrasonic detectors that automatically slams on your brakes when you get in with a certain range. Well, all these range detectors on these new cars are nothing but ultrasonic sensors. So these are ultrasonic sensors. I'm going to try to order some of these just to play around with them. Then we also have, we do have some ultrasonic sensors that I'll have to show y'all. Y'all need to remind me that's on the Lego robot that we have. It has ultrasonics on it, and it actually can measure distance. And I'll show y'all one of the things that we have set up where it appears like the robot it can see, but actually it is seeing, but it's seeing through ultrasonic sensors. The other thing that we need to talk about is what they call piezoelectric. Piezo means, by the way, is a term we use for pressure. So piezoresistive means that these devices vary their resistance with pressure. I have a piezoresistive sensor right here. Okay, so this is really cute. The semiconductor is right here in the center. Okay, and what I'm going to do is I'm going to put my ohm meter across it. And let me find my other connection wire. And then hook up a couple wires to it. Now this is another thing that varies its resistance. So we do have to run this through a fixed resistor or a Wheatstone bridge for the resistance to change in resistance, but actually mean something. Let me make sure I got it on the leads. So here's my ohm meter. So let's see how much resistance this thing has. I think this guy, the resistance is pretty high, and we can't even measure this. Okay, so right now my meter is showing an overload. All I'm going to do is come up here and I'm going to put pressure on this. Okay, and it dropped way, way, way down. I don't know what it actually is. It's more than 2K. So right now it's got 720 ohms. I'm going to try to vary my opposition a little bit. So the tighter I squeeze on this, notice the resistance goes down. The less I squeeze on it, the resistance goes up. So this is a pressure sensor. So it's censoring the pressure that I'm applying to it. Okay, so I'll put it on top of my meter. And I'm going to come over, all I'm doing is just pressing down on it. And the resistance goes down, and I'm going to release some of it, and the resistance goes up. This guy responds really, really fast, too. It's a pretty good pressure sensor. So what we're doing now is we're taking a pressure, and remember, to get a force, we have to have a pressure. So this would be a way we could use this to measure weight. We could use it to measure pressure pushing up against a glass. We could use it making all types of measurements. But this is a piezo resistive pressure sensor. Piezo means pressure. Resistive means it varies its resistance with pressure. Okay, piezo resistive. We could combine these with other type of sensors, and so sensing pressure is very, very important, because pressure is what we need. Pressure to get force. Force causes things to move. So if you exceed if you put too much force on something or too much pressure, then something's going to move. Your windows are going to break out. They put these sensors, they call them strain gauges, but these are pressure sensors that sense that, and they put them on beams in buildings and everything, so they can measure the force and everything applied to those buildings. Piezo resistive. Piezo resistive. This is using to measure the pressure of some type of a vacuum, or pressure on one side, vacuum on the other. The piezo resistive guy would be in the center, right here. Okay, and this would be measuring the differential pressure between the pressure relative to a vacuum. These are just some pressure piezo resistive pressure sensors you can buy. This is another piezo resistive pressure sensor. This actually came, this is a pressure switch. So this, I don't know exactly how this operates. This actually came out of my compressor at the house. What we're going to do is we'll go ahead and I'll start the upload on this one. This will be part one. Part one deals with the resistors, the sensors that are covered inside of chapter, what chapter was that? Chapter 8, I can't remember. And then what we'll do is we'll put a part two. I'll record a part two now and give you the photoelectric sensors that are covered up in chapter 15. Now we're only going to do a small portion of chapter 15.